So I have here two copies of a one-dimensional space, the blue lines, right, with dots and lines, and then another copy above it. And then I'm going to indicate with the arrows immediate successors in time. And in this diagram, what I've decided is that each zero element will have only one successor in time, and each one element will have only one successor in time, which are given by these vertical arrows. So that's one way to add time in. But that's a really bad way to add time in, because what I would like to do is to say things like this, that particles have to travel along continuous trajectories through space-time. And by a continuous trajectory, I now mean always to an adjacent point, always following the arrows. But if there's only one arrow from every point, then everything's going to be frozen. If I have two particles that are right next to each other, they'll always be right next to each other if they're in this structure. So I can do that. It's sort of what you might think of, if you're familiar with this, as a kind of discrete version of Newtonian absolute space and time. It doesn't do me any good. It's not useful. All right. Well, having only one successor isn't good. I can go to the other direction, extreme, and have an infinite number of successors. I could say, well, let me draw an arrow from every single point in one layer to every single point in the next layer. So as it were, every point in the next layer is an immediate successor. And you would get something that sort of looks like this. You see it gets very, very messy. And now there's nothing like a restriction on relative velocities. That is, if I have two particles that are right next to each other at one time, at the next time step, they could be as far apart from each other as you like. They could have separated any amount. This is the kind of discrete version of what we call neo-Newtonian or Galilean spacetime, if you're familiar with that terminology. That's also not what we want. Because one thing we know that relativity has in it are light cones. It has a light cone structure that somehow restricts how particles can move. And this wouldn't have any restrictions. So I don't like that either. Well, one doesn't work and infinitely many doesn't work. I have a whole, lot of things in between. But it turns out that what works really nicely, as we'll see, is the next simplest thing, which is just for each event in this 1+1 dimensional spacetime to have exactly two successors, right? So you can, as it were, either move to the right or move to the left, up one and then move to the right or move to the left. And then from point A here, you get something that looks kind of like a light cone. If from point A, you always have to follow the arrows, you'll always stay within a certain wedge that goes out diagonally. And you'll notice there's only one path. We can now talk about connectivity, path connectivity, by which I mean how many continuous paths connect a pair of points. So from A, there's only one way to get to D. I got to go through B. But from A, there are two different ways I can get to E. I can go A, B, E, or A, C, E. So this, again, is just because this is discrete, I can just count and look at the number of paths. So this is going to turn out to be an absolutely essential quantity in this theory. In this discrete theory, you have a counting measure. You can count the number of continuous paths that connect any two points or any two n elements. And that's going to give you a finite number. Could be 0, could be 1, could be any number, any finite number above that. Now, how do I count these paths? Well, let's just look at the 1+1 dimensional case. It's familiar. Everybody knows this from Pascal's triangle. Pascal's triangle is just essentially counting continuous paths from the apex down to any point in the middle. So if I start at the top of this triangle and I go down to one of the, well, at the bottom, one of the ones marked 15, there are 15 different ways to get from the top down there. You're essentially just counting paths. Now, there's a lot I could say about 1+1 dimensional spacetime, but I want to go to 2+1 dimensions. I don't have much time left. I'm getting really to the point. in 2 + 1 dimensions, what do? Well, the two-dimensional space is our taxicab space. And I'm going to do the same thing. I'm going to take the space, I'm going to take a copy of it and kind of shift it so that the middle of one square is above a dot below it. And then from each point below, I'll draw exactly 4 arrows out to the corners of that square. So I get this kind of truss system. Here's how it looks from above. The crosshatched ones are below, the solid dots are above, and you'll notice from every crosshatched one, you have 4 arrows going out in 4 different, as it were, in 4 different directions. Good. And then I can just build that up into a huge discrete space-time structure. Now I want to talk about path connectivity in this structure. How do I count the paths between things? Instead of using Pascal's triangle, you use this thing called Pascal's square base pyramid. It's a nice thing. I was unaware of it until I started doing this. But just imagine I have a bunch of cubes and I'm stacking them up on top of each other as here. So each cube rests on 4 below it, and that rests on 4 below it. And again, I just want to count the number of paths from the apex down to any cube. I just add the numbers that are above and work down that way. It's a little hard to see in 3 dimensions, but if I go down 5 levels in this pyramid and cut through it, this is what I would see, level 5. Of course, along the 4 corners, there's only one path that goes down. I've always got to go down that edge. But the other things you notice about this is it has 2 interesting features. One is that along each edge, you have just Pascal's triangle. Those are the numbers from Pascal's triangle, which if you think about it a minute, has to be, because in order to stay along the edge, you always have to move in one of the ways you can move. You always have to keep moving in that direction, so that takes it out. And then the other interesting thing is you notice this is a multiplication table, right? That is, the numbers in the interior you just get by multiplying the numbers along the edges that intersect. So the 24, you'll notice, is at the intersection. If you go up to the top, say you get a 4, and go to the side, you get a 6. So it's just a multiplication table with the usual Pascal triangle numbers along the edges. Now, suppose this gets really big, as you would expect. If space is discrete, the level of discreteness is very, very fine. Everyday things are many, 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 many levels up. And we need to make a calculation about this. And we're going to use Stirling's approximation, which is a good approximation to the proper numbers you get out of Pascal's triangle. As those numbers get large, you get closer and closer to a Gaussian distribution, which I've given you here. And the main thing about it, I want to calculate path connectivity. I know how to do it. I use Stirling's approximation for these numbers, which goes to a Gaussian, which I've given you. And if I ignore the normalization constants, it's just e to the minus x squared. So along each edge, the numbers distribute like e to the minus x squared, where x is the distance from the center of that out toward the side. And therefore, for 2 + 1 dimensions, I have the connectivity at any given level will be some constant, e to the minus x squared times e to the minus y squared. And that's e to the minus x squared plus y squared. Now, what you have to notice about that is that it tells you that on a given level of this, the connectivity to good approximation goes as x squared plus y squared. So any 2 points where x squared plus y squared are the same number, the path connectivity will be essentially the same. But x squared plus y squared is the formula for a Euclidean circle. So at the level of path connectivity, strictly Euclidean structure is emerging from this underlying structure that's as non-Euclidean as you could imagine. The underlying structure has preferred directions. The underlying structure, again, the things that kind of correspond to circles are really quadrilaterals. But at the level, once I put time in and I look at path connectivity in time, what emerges strictly is Euclidean structure with no preferred directionality. And it gets better. That's what happens if I look at path connectivity and I cut through my space horizontally. If I cut vertically in a 1+1 dimensional space-time, in Minkowski space, the main structure, the structure of proper time, the structure that defines relativity, is going to be a hyperbola, which is given by the quantity delta t squared minus delta x squared equals constant. And if we look at path connectivity in that way, I haven't been able to derive it as cleanly, but I've done it numerically. Here's the exact formula. If I go up to level n, and I'm counting x from the center point and x and y from the center points, this is the exact formula. And I can actually plug that in and get numbers. So if I go up 800 levels and I look at the very center and calculate the path connectivity, I get this number, 3.5 times 10 to the 478, right? That's big numbers because of the combinatorics. But just remember that, 3 point something times 10 to the 478. So that's a dead center 800 levels up. Now, suppose I go 10 more levels up to layer 810, and I want where I have to move out from the center to get down to that connectivity, because the connectivity is going up along the center. How far out do I have to move along the x-axis? Well, you just fool around with it and you find the best approximation you can get is this one where I go out 75 units, and there I now have 3.1 times 10 to the 478. So the path connectivity from 800 to 810 75 0, 800 00 to 810 75 0 is essentially the same. What if I go out along the diagonal? So instead of going out along x, I go equally along x and y. The nearest point is at 53 out, and that gives me 3.3 times 10 to the 478. So the points 0, 75 and 53, 53 have about the same path connectivity. And you'll notice that the square of 75 is almost exactly the sum of the squares of 53 and 53. Again, the Euclidean circle is emerging. But now I can ask another question, and I'm really almost done. In relativity, what I expect are these hyperbolae to show up. And if I go up from 810 now up to 1,000, I go up to level 1,000, and I calculate where a relativistic hyperbola in a continuum would hit that level, I can get a number, right? It's a precise number, 354.6, I round to 355. So in this discrete structure, I'm going to make a guess that the path connectivity, if I go up to level 1,000, should be about the same if I go out 355 units over. And when I actually plug it in, here's the number I get. 3.3 times 10 to the 478. So there's no doubt that relativistic structure is emerging with no twiddling of knobs, with no setting of any free constants, almost precisely. The structure of relativity emerges at the level of path connectivity from this discrete underlying structure that has a preferred foliation. And so if that's what space and time were really like, and if the physics were sensitive to path connectivity, the physics would, as it were, appear to be in a Minkowskian spacetime, even though the underlying spacetime is as far as possible as you can imagine from being that way. Now, that's the end of this story. I will make one more comment. Another nice thing about discrete geometries like this is you don't get singularities. All you ever do are add finite numbers of finite quantities. Things can't blow up. So in terms of cosmology, the Big Bang can't be the beginning. What we would naturally say is that the problems that arise in general relativity of the emergence of singularities can't happen here. The problems that arise in quantum field theory of the emergence of singularities can't happen here. And so you would expect that the space-time structure should continue back, and you should be able to figure out what was going on back before the Big Bang, if this is what's going on at the fundamental level. So